Good morning, everybody. We are going to get started with this week's planetary sample science seminar. I'm Lydia Hamilton. I'm a master's student here at UNM, and it is my privilege to introduce our speaker today, Nick Dygert. He is an experimentalist and geochemist interested in the evolution of planetary interiors. He was an undergrad at the University of Rochester and then earned his PhD at Brown University before moving on to a postdoc at the University of Texas at Austin. Welcome. Nick started his faculty appointment at the University of Tennessee in 2017 and was named the Lawrence and Dawn Taylor Chair in 2019 and was promoted to associate professor in 2023. Nick is on sabbatical this term and will visit Woods Hole Oceanographic Institution to work with methods to experimentally constrain non-traditional isotope fractionation factors. So Nick, I will hand it off to you. We can see your slides. So take it away.
Okay, great. Thank you. Can you see the laser pointer? Just curious.
Yeah.
Okay. Excellent. Thank you for the introduction, and thanks for inviting me to give this talk. I'm excited to talk about some recent results that some graduate students and I have produced that I think are interesting, and they really provide some new insights into the relationship between the lunar crust and the magma ocean, and the evolution of the lunar crust after the magma ocean stage. And really, all of these results relate to trying to quantitatively model rare earth element patterns. You see here chondrite normalized rare earth element patterns for plagioclase in ferro anorthosites returned by Apollo and lunar meteorites as well. And so by investigating the slopes of those patterns and the magnitude of the europium anomaly exhibited by these samples and relating it to magma ocean solidification, we can learn some new things about lunar evolution. I want to start out here with an introduction of this important phase of lunar differentiation, which is magma ocean solidification. So the moon is thought to have formed after a giant impact that produced a moon that was entirely molten or partially molten initially. And so these cartoons show different stages of solidification of that initially molten moon. The first phases that would have precipitated from the magma ocean are dense olivine and orthopyroxene cumulates, and so these would have settled out around the core. And because the elements calcium and aluminum don't substitute appreciably into those phases, the residual liquid in the magma ocean would have compositionally evolved. And after about 80% solidification, it's thought that the magma ocean would have become saturated in anorthitic plagioclase, which is buoyant on a magma ocean liquid. And so that would have floated to form a stagnant lid protocrust and dramatically slowed down magma ocean solidification. But nonetheless, it would have proceeded at a slower rate and continue to precipitate mafic phases and eventually become highly enriched in incompatible trace elements, among them potassium, rare earth elements, and phosphorus. And so you've heard this CREEP acronym. It just refers to a characteristic trace element pattern exhibited by many lunar samples that's thought to have originated in this end stage of magma ocean solidification, where there was this concentration of these incompatible elements in the residual liquid. So we're going to come back to thinking about the importance of CREEP for the lunar crust later. All right, and then the last solid cumulates that would have precipitated from the magma ocean included things like iron titanium oxide, ilmenite, which is dense, and would have produced a second stage of differentiation called cumulate overturn, which I don't have time to talk about today. So I'm really going to focus on the anorthositic crust and its relationship with CREEP and the evolution of the crust. after the magma ocean stage. And so in some sense, this talk is backwards. So first I'll talk about the relationship between the lunar crust and the magma ocean, and then the evolution of the crust after the magma ocean stage. And then in a second part of this talk, I'm going to return to thinking about the magma ocean processes and investigate the efficiency of plagioclase flotation on the magma ocean during solidification. Okay, and so the first part of this talk is a summary of results that were published in a recent paper that came out in EPSL. And the first author is Dion G, who's now a PhD student at Rice. I encourage you to check out that article if you'd like to read more about these models. Okay, so just briefly, this figure summarizes the mineralogy of primary lunar crust. So these are pure, relatively pure anorthosites returned by Apollo, the ferro anorthosites. That's what the FAN acronym refers to. And here you see the mineralogy. In this ternary diagram, the apex here is plagioclase, high calcium pyroxene, and low calcium pyroxene on the other corners. And you see that these samples have a very high plagioclase mode and a minor pyroxene fraction. And this is really remarkable to igneous petrologists who study rocks on Earth, because there are almost no rocks on Earth except cumulates that form in very specific settings that are so mineralogically pure. And this was one of the primary pieces of evidence used to infer a magma ocean on the moon. It really requires physical separation of plagioclase as it precipitated from the parent liquid. And so that flotation process on the magma ocean is what could produce that. So these mineral modes, they're going to be important later in the talk. So remember that, well, the anorthosites are nearly pure. They do contain this minor mafic component. And now I want to return to looking at the rare earth element patterns. So these are characteristic patterns exhibited by ferro anorthosites and lunar meteorites as well. And these might come from different places on the moon. The ferro anorthosites were all returned from the near side. Those lunar meteorites sample presumably the entire moon, so more representative of perhaps the far side. And there are a couple characteristic features of this pattern that I want to point out. I guess first of all, I'll mention that these elemental abundances are chondrite normalized, so that is just a convenient way to remove nucleosynthetic anomalies from elemental patterns, so that anomalies with geologic significance can be understood. And so here what you see is a downward sloping pattern in terms of light to heavy rare earth elements. So the light rare earths are more enriched relative to the heavy rare earths. And then there's this prominent positive europium anomaly. So the rare earths are trivalent except for europium, which is partly divalent under lunar relevant oxygen fugacities, which is what produces that anomaly. And I'll go into that in a little more detail on the next slide. So in order to understand the significance of these elemental variations, petrogenetic models have to be developed to quantify elemental fractionation during magma ocean solidification. And so these rely on mineral melt partition coefficients. Here's the definition of a mineral melt partition coefficient. I, the superscript I, refers to the element, and you see here the concentration of the mineral is divided by the concentration in the melt. So these mineral melt partition coefficients can be experimentally quantified, and then if the concentration of an element in a mineral or melt is known, the concentration in the corresponding phase can be solved for using the definition of the partition coefficient. Partition coefficients are composition dependent, pressure dependent, temperature dependent, and in the case of europium, oxygen fugacity dependent. So elements that have partition coefficients greater than 1 are called compatible. And for these elements, they prefer to substitute into the crystal. So the case of europium, this is a compatible element. It would rather substitute into the plagioclase structure than into coexisting silicate liquids. The other rare earths are incompatible. They have partition coefficients less than 1, and so they prefer to reside in the residual liquid of the magma ocean, which is why they accumulate in those later stages. And actually, the slope of the rare earth element pattern that you see reflects the variation in partition coefficients among the rare earths according to their ionic radius. Okay, so here I'll briefly talk about why europium partitioning behavior differs from the other rare earths. I already mentioned that it partitions differently according to oxygen fugacity, and that's because it's a multivalent element. So under geologically relevant conditions, it can have a 2+ valence state or a 3+ valence state like the other rare earths. And this figure shows the relative proportions of those species as a function of oxygen fugacity. And this is kind of a weird figure because this is the negative of the log of the oxygen fugacity. So log units of oxygen fugacity. So these are low oxygen fugacities, and these are high oxygen fugacities. And so you see the proportions that there's more divalent europium under reducing conditions than under oxidizing conditions. So I guess I should just briefly mention that oxygen fugacity, it's an important term you're going to hear throughout the talk, and that's the effective partial pressure of oxygen in the system, and it's often abbreviated as FO2. Okay, so europium speciation is FO2 dependent, and that affects the ionic radius of europium. So here are ionic radii of rare earth elements as a function of their atomic number. And you see that divalent europium is much larger than trivalent europium. So not only is the valence state different, the ionic radius is different under reducing conditions for europium, and that affects the partitioning or substitution behavior. So we already saw that europium was FO2 sensitive in terms of its valence and ionic radius. For a long time, going back to pioneering work by Mike Drake and others, people have investigated the effect of this oxygen fugacity dependence on its partitioning behavior. So here is a nice suite of experiments by Wilkie and Behrens. And so they investigated plagioclase melt partition coefficients as a function of FO2 for different types of silicate liquids. And actually, these are a highly silicic system at different temperatures and pressure conditions. And they and many others have observed sort of the sinusoidal variation in the partition coefficient with oxygen fugacity, related to that change in valence state and ionic radius, with plagioclase strongly preferring the more reduced europium species. And so this is what produces that large positive europium anomaly that you see in the patterns exhibited by the meteorites and the ferroanorthosites. So what I'm going to try to do here is evaluate the significance of that europium anomaly quantitatively. And what I'm going to do, the composition spacing I'm going to use to do that, rather than evaluating the entire rare earth element pattern, I'm going to boil it down to 2 features. So on the y-axis here, I've plotted these same data as the cerium-samarium ratio. So that's just the slope of the rare earth element pattern. And then the x-axis here, this is the europium abundance divided by europium star. So europium star, that's the interpolated anticipated europium abundance according to neighboring elements on one of these rare earth element diagrams. So that's samarium and gadolinium in this case. So the europium over europium star indicates the sign and the magnitude of the europium anomaly. So values greater than 1 are called a positive. And of course, the larger the value, the the greater the magnitude of the anomaly. All right, and then the color scheme will be the same for the samples that you've seen in these rare earth element diagrams. So the ferronorthites are black symbols, and the northitic meteorites are blue. Okay, so where we're going to get to is modeling europium fractionation during magma ocean solidification. How do we do that? Using these mineral melt partition coefficients, and it's now possible to evaluate europium fractionation during magma ocean solidification in a more generalized way, thanks to this model that I worked on with several co-authors to be able to predict europium partition coefficients as a function of temperature, composition, and oxygen fugacity. And the predicted model has this form, equation of this form, and we'll walk through that, how that's derived in a minute. But just on the right here, here are partition coefficients predicted using this model at 1200 degrees C for two different plagioclase compositions, one that's more sodic and one that is more calcic. And each of these colored lines corresponds to a different oxygen fugacity, the black line being more reduced. And you see the more reduced the sample, their system is, the larger the europium anomaly is. So this is an equation that has been widely used in the past. It goes back to at least the early 70s, but I think it's useful to walk through the derivation. So first of all, so it's not a black box, and so you could see how you could use these same assumptions to develop multivalent partitioning models for other elements. So you can write a redox reaction, in this case for reduction of trivalent europium to form divalent europium, and define an equilibrium constant for that reaction. In the numerator, here we have the products, the activities of the products, and in the denominator, the reactants. Break the activities into mole fractions and activity coefficients, making the simplifying assumption that the activity coefficients are equal, they cancel, and we're left with the mole fractions in the numerator and denominator, and then converting those to mass fractions. The conversion factor in the numerator and denominator cancels, and we're left with this expression. Then defining the total europium partition coefficient, right? You saw the definition, the more general definition of the partition coefficient. This is for multivalent elements. So here we have contributions of the reduced species, the mass fraction of the reduced species, and the oxidized species in the plagioclase in the numerator, and then in the denominator, the same species in the coexisting liquid, and rearranging this equation and this one and combining them gives this expression, where the europium partition coefficient is a function of an equilibrium constant, the reduced and the oxidized species, and oxygen fugacity. And this equation, this is useful for petrogenetic modeling, but it can also be useful in oxybarometry. You could measure the europium distribution, between a glass and a coexisting plagioclase crystal, and if they're in equilibrium, and you can predict these divalent and trivalent partition coefficients, and you can calculate oxygen fugacity. And so that's something I've done looking at plagioclase hosted melt inclusions for mid-ocean ridge basalts. And I think there's a lot of potentially fruitful results that could come from doing the same thing to lunar melt inclusions. But anyway, in this talk, mostly I'm going to be working with this equation. So I mentioned that two important parts of this predictive model are divalent and trivalent europium partition coefficients. So these have to be predicted, right, in order to calculate the total europium partition coefficient as a function of FO2. And that's possible thanks to some very accurate and precise predictive models that were developed by Chen Sun. And these models make it possible to predict partition coefficients as a function of the anorthite content of the plagioclase, basically how calcic is it, the temperature and the pressure. And over here on the right, you see for the calibrating data, predicted partition coefficients plotted against measurements for divalent and trivalent elements. So this accurate and precise model can be leveraged to develop a model for the total europium partition coefficient. So that's an important model input. And obviously the other one is this equilibrium constant. So using published experimentally determined partition coefficients or experiments conducted under controlled oxygen fugacity conditions, I inverted the equilibrium constant. And I just want to briefly show you here the compositional ranges from which those partitioning data were determined. Here you see the plagioclase anorthite content, again, how calcic is the system, and the x-axis here is the silica content of the liquid. So there's quite a large range of anorthite contents, at least in terms of terrestrial and lunar relevant compositions. Now I'm working on abrites, and unfortunately they're compositionally down here. So we may have to run some new partitioning experiments to explore behavior in that system. But anyway, this model should work well for these lunar relevant conditions. And there's also the Mg number, magnesium to iron ratio of the silicate liquid. Okay, so quite a large range there. All right, so applying this model to the experimental data returns this equilibrium constant, which is similar to values determined for several other systems. And on the right here, I plotted on the x-axis measured experimentally determined partition coefficients, and on the y-axis are the predictions. And the colored symbols there, those are the calibrating data, and then the gray symbols in the background, those are an extrapolation data set. So, I wish the model were more accurate or more precise, but it is accurate, and it's accurate over 15 orders of magnitude of FO2 variation. And you saw that compositionally, these data span a very large range, so they're dacitic to basaltic systems. So this model should be very generally applicable and certainly lunar relevant, as many of these partitioning data were collected specifically for lunar systems. Okay, so that's how the europium partitioning model was developed. Returning to the motivation here, the goal is to understand how europium would be fractionated by magma ocean solidification and relate it to lunar samples. And that is possible thanks to some very labor-intensive experimental work that several groups undertook, over the past decade or so, and published, I guess, coming out now 7 years ago for the most part, although more recent study came out of the group in Switzerland. But in any case, these different studies investigated the solidification sequence for different bulk moon compositions of the magma ocean. So in particular, these studies investigated bulk moons that have an enrichment in refractory calcium and aluminum. So these produce more plagioclase. Other bulk moons are more similar to Earth's upper mantle, like the LPUM model, and produce slightly less plagioclase. And I'll just point out, we don't have time to go through all the details here, but you'll see that the solidification sequence is more or less consistent among all of these studies, regardless of the bulk moon that was assumed, at least in terms of the mineralogy and the variation in the mineral compositions as well. So we explored europium fractionation for all of these different solidification sequences and found that it wasn't significantly different, comparing even, say, a Taylor whole moon to an LPUM bulk moon. And so just as a representative example, I'm going to show you here cases for an LPUM bulk moon. All right, so implementing that europium partitioning model for plagioclase and a lot of other very conscientiously developed predictive partitioning models for lunar systems, makes it possible to calculate the composition of the residual liquids in the magma ocean, and then also the solids that precipitated from that magma ocean liquid as a function of the extent of solidification. So you can note a few things here. One is that initially the bulk moon has this chondritic rare earth element pattern. As solidification proceeds, you can just start to see the change in slope of that pattern. So you see that downward sloping trend in terms of the rare earth elements, and that's because the light rare earths are more incompatible in the solids that are precipitating from the residual liquid. So they accumulate in the residual liquid. And then, of course, you also see the development of a negative europium anomaly. And the onset of that is when the magma ocean is plagioclase saturated. So the plagioclase takes most of the divalent europium out of the liquid and sequesters it into the crust. And of course, there's also a negative europium anomaly in the mafic cumulates that pile up at the base of the magma ocean. Okay, so finally, getting on to comparing these model predictions to the natural sample variations, we got a very surprising result, and that is that the europium anomalies and rare earth element pattern slopes of the modeled plagioclase that precipitated from the magma ocean are inconsistent with the lunar samples. All right, so again, here you see the cerium-samarium ratio, the slope of the rare earth element pattern for the plagioclase. The x-axis again is the europium anomaly. All right, the black and blue circles, those are the natural data, and then the red, yellow, and green circles, those are the predicted compositions of magma ocean cumulate plagioclase. So these are predictions made at 3 different oxygen fugacity conditions. So the green and the yellow dots, those are for oxidized cases that are not relevant to the moon. Those are relevant to Earth. So Earth's mantle today has an FO2 close to the FMQ buffer. But the moon is much more reduced, probably 4 orders of magnitude or more reduced than Earth. And the most lunar relevant condition here is this iron wustite -2 case, shown in red. And you see that for that case, the predicted plagioclase have much larger europium anomalies than the distribution of samples. And then, of course, the pattern slopes of those plagioclase, they overlap a small number of the data, but the majority of the data have steeper pattern slopes than these predictions. So, this was a little bit of a disturbing result. Initially, I thought there was a problem with the partitioning model or the calculation. I tried it multiple ways with different codes and kept reaching the same conclusion. And so then the question was, is this a problem with the lunar magma ocean model? Or was there a more complex evolutionary history for the anorthosites? And so we went ahead and tested different scenarios to evaluate whether that second possibility were true. And so I'll walk you through them now one by one. So the first scenario we investigated was partial melting of the primary flotation crust. Could partial melting, perhaps driven by impact bombardment or some sort of thermal anomaly that infiltrated the crust, could that have produced this distribution of data? Of course, partial melting of the crust only increases the europium anomalies of the plagioclase because europium is compatible in plagioclase. So it's sort of like a zone refining process that ends up just increasing the europium in the crust. So that doesn't help. That didn't work. So then we started thinking about subsolidus reequilibration. So this is something that it's a very important process, particularly in metamorphic petrology. And it's something that often isn't modeled by igneous petrologists because it requires understanding the temperature-dependent distributions of elements under subsolidus conditions. So, if you have this system containing pyroxene and plagioclase in equilibrium, you lower the temperature. How are the elements redistributed in that process? Diffusively. And the way that we were able to model that is by simply taking the ratios of pyroxene melt and plagioclase melt partition coefficients. You remember the definition of the partition coefficient has the melt term in the denominator for both of these. And so these terms cancel. And so by taking this ratio for the pyroxene and plagioclase melt, we can calculate two mineral partition coefficients that can then be extrapolated to subsolidus conditions. And then writing out a mass balance equation, substituting in the partition coefficients, it's possible to calculate the concentrations as a function of those temperature-dependent two mineral partition coefficients and the phase proportions. Okay, so doing that produced this grid that you see now superimposed over the data. So the rows in the grid, these correspond to different temperatures. So temperature for an initial composition down here will drive you up and to the right, and increasing oxygen fugacity drives you to the left in this space. So we see here that subsolidus reequilibration really expanded the domain of chemistry that could be produced, but still for these lunar relevant cases with low oxygen fugacity, the predictions don't overlap the data. Nonetheless, this seemed like a promising direction to go. So we then tried adding different components to our plagioclase flotation crust, or an orthocytic flotation crust, and then superimposing subsolidus reequilibration on top of that. So the first that we tried was adding a trapped lunar magma ocean liquid component. So you can envision that you might form, say, a clump or a clot of plagioclase in the magma ocean that would float up, and along with it would be some rafted magma ocean liquid. It turns out that adding trapped magma ocean liquid, it does drive this grid over more of the data, but you have to add an unrealistically large amount of lunar magma ocean liquid in order to produce a significant change in the trace elements. And you'll remember that the mafic phase proportions in these samples were low, right? In most cases, there are only a few percent mafic phases. And so that suggests that you can't add such large proportions of trapped lunar magma ocean liquid. So this didn't work. Then we tried adding a chondritic component. You know, the moon is constantly suffering impact bombardments. Maybe adding a chondritic component is a reasonable thing to do. It doesn't do enough in terms of shifting the composition over the natural samples. So then finally, we tried adding a minor creep component to this system, and then imposing the subsolidus reequilibration on top of that. All right, and for our creepy component, we chose a representative creep basalt, but we're agnostic about what this creep component is. You know, it could be an Mg sweet liquid, it could be a creep basalt. It just has to have a creepy trace element pattern. It has to be enriched in rare earth elements. But adding a very minor amount of creep shifted this grid over the bulk of the data. So the solid lines here you see are for a case where we've added just 0.25% of a creep component. And then in the background, the transparent case, this is where 2.5% creep was added. So adding the creepy component and superimposing subsolidus reequilibration on top of that can reproduce all of the compositions of the natural plagioclase. So then we were interested in exploring what sorts of different combinations of conditions could reproduce the natural sample distributions. And that's because these models are non-unique. You know, you can make different sorts of assumptions about parameters and achieve the same results. And so here you see examples of successful simulations, Monte Carlo simulations, and unsuccessful ones. So the threshold for success was basically the analytical uncertainty of the natural data. So we tested different combinations of temperature, addition of a creep component, and oxygen fugacity, and we also tested different bulk moon compositions. And here are histograms showing the results for a case where, I think this is for a chondritic bulk moon case. We've we've separated ferroanorthosites from lunar meteorites. So here you see temperatures of successful simulations. The most successful simulations invoke temperatures between about 1050 and 1250, depending on the samples. It's interesting that the meteorites seem to record higher temperatures. And of course, these are physically unrealistic cases off here on the right, where you'd have a molten crust. But we wanted to explore as much possible range of these input parameters. Here you see the oxygen fugacity conditions that can successfully reproduce these compositions. So in most cases, the FO2 is about iron wustite -2, and then the creep component that was added, it's generally less than 1%, in some cases as much as 2%. So these are the compositional ranges that we can use to then try to understand, what conditions could have formed or produced this subsolidus reequilibration that seems to be required to have evolved the lunar crust after the magma ocean stage. And I will say, we actually found that a slightly depleted bulk moon produced a larger number of successful simulations than a chondritic one, but both cases worked. And I'm not going to go into the implications of how the moon might be slightly depleted, but I'm happy to talk about that after the talk, if anyone's interested. All right, so these conditions led us to propose that there had to be some mechanism for thermally metamorphosing the crust, and at the same time, or prior to that, injecting this minor creep component. So there are several possible scenarios that could produce this. If you were at LPSC, there's a good chance you saw Francis Nimmo's talk on tidal heating of the moon and the lunar crust, and he was interested in trying to understand the overlap of ages of the secondary crust and the primary crust, and he invoked tidal heating to do that. Well, tidal heating would produce thermal metamorphism, of course, as well, and potentially redistribute rare earth elements. We also considered the possibility that there could have been magma injection after cumulate mantle overturn, the second stage of lunar differentiation, which would juxtapose hot cumulates with the base of the crust. And this has been long been invoked as a mechanism for forming a very pure crust. You might have heard of the serial magmatism hypothesis, and that was developed by John Longy and others. So that's similar to what we're proposing here in this cartoon. I think to evaluate which heating mechanisms are realistic, this is going to require coupled thermal and closure temperature modeling. So the geodynamicist needs to work on that. And then an interesting point is that, these, especially the ferroanorthosites, they come from the surface of the moon, but they record very high temperatures, 1050 to 1250. That means that the moon had to be resurfaced, right? They had to have come from the deep lunar interior, perhaps the mid-crust or the lower crust. And so, of course, that's going to require impact gardening or perhaps resurfacing by diapirism. All right, and then the last implication here that I've already alluded to is that subsolidus reequilibration could reconcile the overlapping ages of secondary crust and the inferred primary crust. And if you're not familiar with the data, here's a nice summary from a paper by Lars Borg, where he shows these ages determined for Mg sweet rocks. This is the secondary crust, and the ferroanorthosites. The x-axis here is the age, these being older, and you see there's near complete overlap among the samples, which is impossible owing, to superposition. These Mg sweet rocks formed by injection into the ferroanorthosites. So this thermal metamorphism could reconcile these data. Okay, so moving forward now, what we're going to evaluate another aspect of formation of the crust, and that is the efficiency of plagioclase flotation during magma ocean solidification. Okay, so returning to thinking about the influence of plagioclase fractionation from the magma ocean on the chemistry of the moon, we can take a look at the compositions of basaltic glasses. So here are low titanium picritic glasses, high titanium picritic glasses, and crete basalts. You see that all of these sample types have this large negative europium anomaly. So this is conjugate to the positive europium anomaly in the lunar crust. And it suggests this is good evidence for plagioclase flotation on the lunar magma ocean as a mechanism for depleting the sources of these basalts in europium. And so an interesting question that petrologists have been wrestling with for several different reasons is how efficient was that plagioclase flotation on the magma ocean? So these are two different cartoons that just highlight two different possible end-member scenarios, where on the left you see very efficient crystal fractionation, where plagioclase that's precipitated floats according to its density, and dense mafic phases sink according to their density. And then in the case on the right, perhaps owing to more vigorous convection or heterogeneous nucleation or clumping of crystals, you have a scenario where there's a much dirtier cumulate pile forming at the base of the magma ocean, where a significant amount of plagioclase ends up in the floor. And that can be investigated geochemically by quantifying the europium anomalies in the basalts. Okay, so in order to do that, we had to model the formation of the sources of the lunar basalts. And of course, to do that, we used a magma ocean solidification sequence. And here we looked at the sequence for an LPUM bulk moon by Charlier. These are the different layers that formed during magma ocean solidification, and note they're numbered. So layer 1, these are the first cumulates that precipitated olivine. Layer 2 is composed of olivine and orthopyroxene. Then in layer 3, there's a low calcium pyroxene pigeonite and plagioclase saturation, and then more and more exotic phases as the composition of the residual liquid evolved. Okay, so in order to model the formation of these sources, which are thought to comprise different combinations of these layers that precipitated from the magma ocean, we had to carefully model the europium abundances in each of these layers. With the crust, we were able to get away with focusing on plagioclase because it's so dominant in fractionating europium. Here we're not only modeling the influence of plagioclase on these basalt sources, but all these other phases as well. And in some cases, there were FO2-dependent partitioning models that had been developed that we could use that were published in the literature. In other cases, there weren't for some phases, specifically for olivine and for ilmenite. And so we had to develop new predictive trace element partitioning models for those phases. And we used the lattice strain model as a framework. Then on the right here is the schematic showing how the lattice strain model works. So it parameterizes the variation in partition coefficient for isovalent elements that have different ionic radius as a function of 3 different properties of the lattice site. So there's an ideal strain-free partition coefficient, which determines the apex of this parabola here, right? There's an ideal ionic radius, which shifts the parabola left or right, and then an effective Young's modulus term, which describes the stiffness of the parabola. So basically, if an ion's too big or too small, it's a misfit for the site. And so this model determines the penalty, the substitution penalty, that is going to decrease the partition coefficient correspondingly. And so in order to develop these predictive models for europium, for olivine, and ilmenite, we had to understand how divalent europium would partition into those phases as a function of composition, pressure, and temperature. And my student Jesse compiled all the partitioning data he could find and was able to develop very simple expressions for these lattice strain model terms that enable prediction of divalent element partition coefficients very accurately. And using this model, we can make an extrapolation and predict divalent europium partition coefficients that haven't been measured. All right, he went through the same exercise for ilmenite. And again, we can calculate the divalent europium partition coefficient for that phase as a function of pressure and temperature. Then those predictive models were implemented in equations, with the same form that we walked through the derivation of. And Jesse calculated an equilibrium constant for these phases using partition coefficients that were actually measured for olivine. Unfortunately, there weren't enough data for ilmenite for him to calculate the K term using the partitioning data, but he was able to make a reasonable assumption that is going to be accurate to first order. Okay, and so then with these models, he calculated partition coefficients for magma ocean solidification as a function of oxygen fugacity. So these figures show the europium partition coefficients for different phases as a function of FO2 for an early stage of magma ocean solidification and for a later stage of magma ocean solidification. So note the partition coefficient variations with FO2 differ. So olivine and ilmenite both decrease as FO2 decreases, but clinopyroxene increases as FO2 decreases, at least at this temperature for this particular composition. Note at a lower temperature, there's no appreciable variation in the europium partition coefficient as a function of FO2. So thinking about fractionation of europium from the magma ocean liquid becomes a very complex nonlinear problem where you have the contributions of all of these phases potentially fractionating europium in different directions at different times during magma ocean solidification. All right, but here what Jesse did was he plotted europium anomalies of the cumulates that formed from magma ocean solidification for two different FO2 cases. So for an oxidized case in blue and in red there, a reduced case. All right, and each of these line styles corresponds to a different layer. So these are the first layers that precipitated from the magma ocean. You see they don't exhibit significant europium anomalies, at least for that first layer. The second one is slightly negative. And then looking at the later stages of magma ocean solidification, Jesse calculated the europium anomalies as a function of plagioclase flotation efficiency. So if you retain some plagioclase in those cumulates as they form, what is the europium anomaly that's produced in that potential basalt source in the lunar cumulate pile? And so I'm not going to guide you through all these different lines because there's so many different scenarios to explore here. But what Jesse shows is that the minimum flotation efficiency to form mantle cumulates with a negative europium anomaly is FO2 dependent, and that it's somewhere between 60 and 85%, depending on oxygen fugacity and also depending on the layer that's explored. And of course, mantle sources have to have negative europium anomalies to produce basalts that also exhibit negative europium anomalies. The problem becomes more and more complex as you make an attempt to model feasible sources of lunar basalts, but what we've done here is make a reasonable assumption about sources of high titanium basalts. So again, the y-axis here is the europium anomaly that's produced. Average europium anomalies are shown in gray for high titanium picritic glasses, and for these two different sources that Jesse investigated, he found that the plagioclase flotation efficiency, again, was somewhere between 60 and 90%, but there are all kinds of factors that affect the flotation efficiency that is possible according to the glass chemistry. But in some respect, this result is a no-brainer. We can't take a bunch of plagioclase with a positive europium anomaly and put it into a basalt source and maintain a negative europium anomaly in that source. So what we're really doing here is putting lower bounds on the required efficiency of plagioclase flotation. And this has some interesting implications, which we'll get to in a second. I'll just reiterate the results here that Jesse developed partitioning models for olivine and ilmenite, And what was a surprising result to me when we implemented those in magma ocean solidification is that lower lunar magma ocean FO2s actually permit less efficient flotation because of the contributions of all of the phases that precipitate from the magma ocean to the europium anomalies of the cumulate pile. But if we make the assumption that the moon's FO2 is iron wustite, plagioclase flotation had to be more than 75% efficient. Now, relating this to the crustal thickness is interesting. Charlier investigated the thickness of the lunar crust as a function of magma ocean depth for different plagioclase flotation efficiencies. And the case that I just mentioned was 75%, say as a minimum flotation efficiency. So a case relevant to this line here. Okay, the Grail-based crustal thickness, this was determined using gravimetric data and a crustal structure model, suggests that the lunar crust is on average about 40 kilometers thick. So if the plagioclase flotation efficiency is 75%, then the crust would be too thick unless the magma ocean is shallow. And so if this model is right, the conclusion is the magma ocean was shallow or the crust was thinned after the magma ocean stage. And I think the jury is still out on, the accuracy of this model, and we'll have to investigate that further. All right, so this was kind of a whirlwind tour through our investigating work on the distributions of europium and what we could learn about the moon from it. I want to acknowledge funding from my sponsors and the contributions that Dion and Jesse made to this work, and I'll leave you with a couple takeaway points. Thank you.
Thank you so much, Nick. We've got a few minutes for questions. If we've got any, either in the chat, from our online people, or from anybody here in person. I think we're all still absorbing it. Okay, Chip.
Yeah, thank you so much, Nick, for giving this presentation. It was really fascinating. The question I kind of had for you is, what do you kind of gave kind of big picture models for how the crust could interact with a creepy component to modify the europium anomaly and other slopes of the rare earth patterns. How do you really envision that in terms of, do you see that being an interaction, solid state interaction, or an interaction between a creepy magma and a ferronorthosite crust? How does that work? And are there other elements that one could look at to confirm that the europium is telling you the right thing?
Yeah, that's a great question. And I guess what I envision, what we envisioned, when we developed this model, was that it had to be an interaction of a liquid, produced during end stage magma ocean solidification, or and perhaps affected by subsequent partial melting that interacted with the crust as a solid. But the crust had to be hot, for this to happen. We did some back of the envelope kinetic modeling that suggested it could take up to a few 100 million years for diffusive reequilibration to occur, unless we're kind of near magmatic conditions. And so, my personal go-to is to invoke cumulate overturn as something that's potentially capable of driving this combination of processes that had to occur. You can produce the creepy liquid. You might inject this creepy liquid in the primary crust during the process, and then cumulate overturn would bring hot cumulates from the deep lunar interior to the crust mantle boundary that would provide that heat. I hadn't thought much about tidal heating, before LPSC this year, and what I'd like to do is investigate whether these thermal models are consistent with the closure temperatures and the kinetics that are required to make this reequilibration happen. And I think that is something that has to happen for modeling the zircon data as well. So I think there are paths forward in kind of evaluating these different potential scenarios. And in terms of thinking about other elements, I'm sure there are. The challenge is having very accurate partitioning models that can sort of track their evolution throughout all the stages of the process, from the magma ocean to this thermal metamorphism. And, the one that just jumped to mind, when you asked that was scandium, because that can probably be predicted using these trivalent partitioning models, but I haven't looked into it yet.
Thank you. Anybody in the chat have any questions? Probably have time for one more.
Oh, Lydia, I have a question.
Oh, okay. Can you speak, Q?
Yeah. Can you guys hear me?
Okay, yes, we can hear you because we're on the same team.
Yeah, I know we're on the same. So I had my hand raised, but then I realized I guess you couldn't see it. So.
Okay, Quentin, go ahead.
Yeah, no worries. Nick, that was that was like some really awesome implications, especially with the model, with that whole like idea of potentially being subsolidus reactions with creep. I'm wondering, is there anything in the literature that you see that, kind of point to other evidence of this potential subsolidus reaction with creep? Like, is there mineralogical evidence or something like that?
Oh, absolutely. I mean, they're lunar granulites.
Okay.
And I might be mistaken, but I think Chip has worked on those in the past.
So not only can it be useful to
Yeah, I mean, there's just evidence that, for grain coarsening, and these, in some cases, they look like metamorphic rocks rather than igneous rocks, and it's difficult to see through brecciation. But yeah, absolutely. I think the textural evidence is there, and then, of course, to me, this is almost a smoking gun that there had to be thermal metamorphism, unless the magma ocean solidified instantaneously and the MG suite was produced right afterward, within the uncertainties of these ages.
Okay. But like anything specifically in the ferronorthosites that you see, like the ferronorthosites having some kind of creep component in them as well.
Oh, I see what you're saying.
Yeah, because looking at the ferronorthosites themselves, because I know you had mentioned like there were the mafics that are also potentially in the ferronorthosites, but like anything specifically in the fans that we might see that you can point to say, oh, there was some kind of subsolidus reaction with creep in the fan itself.
Well, you can interpret these pyroxenes as being related to that injection of the creep. There aren't more exotic phases though, which actually helped us in this modeling. There aren't things like phosphates that would have completely screwed up the subsolidus reequilibration calculation. So I think there's circumstantial evidence.
Okay.
Thank you again so much. Oh, thank you again so much, and thank you everybody for being with us today. I will see you same time next week.
Oh, and make sure you keep Quentin on, because we're gonna have our discussion.
Okay, so I will see everybody next week. Thank you so much for coming.
All right, thank you everyone.